This should be working. And welcome to those of us who are joining through the recording. This time we're using QuickTime to record everything, so it will be posted on that unlisted YouTube page as soon as we're done with today. So if you have any questions, let us know. In terms of announcements, I was just mentioning it to some of the folks in the classroom. We have the first problem set, which will be released today. It will be released today, but it won't be due for 2 weeks. So you have 2 full weeks to work on it until not this Friday, but the following Friday. And I think it's going to be a good chance for you to test your knowledge, start to work together in teams, start to work together in pairs, and so forth and so on. So that is what will be released today. Andres also will be sending an announcement about the TA sessions shifting a little bit this week due to travel. So that will be another announcement coming through the Piazza. As for the schedule for today, I wanted to start with the R, since I think last time we started with conceptual material, but let's just change things around this time. We'll start with the R material, and we're going to make sure we're all on the same page. We're going to do some new material with that. We're going to introduce you to some things that will be important later on in the semester, and then we will go into some more conceptual material, breaking things down, making things simple, making things hopefully as easy to understand as possible for everyone. So that's the plan for today. So I uploaded new .r files in the link on the Piazza. So they're new .r and .pdf files for the materials for today. So I wanted just to walk through this, and the first thing that I wanted us to do is just go through what we did last time, but I want everyone to just look at the code, and if there's anything at all, no matter how small, that you don't understand, I want us to just talk about it, since if we don't talk about it, then there's a chance that little thing that, it doesn't make sense now snowballs into a bigger thing that doesn't make sense later. So let's just go through almost line by line, and I want everyone just to consider to themselves, or maybe let's have everyone discuss with the person next to them for like 30 seconds. Do you understand everything in this line of code, or do you not? So let's just start here, line like 9 through 13. If you have it up or looking on the screen, does everything that happens within this, make sense, or does it not make sense? And then talk about it with the person next to you, and then we'll go from there. So if you want to talk with the person next to you, is there anything that doesn't make sense, or do I understand every single aspect of it? All right, let's go. Starting now. Do you want to announce those changes today, or will you send Piazza? What's up?
I guess it depends on how they get it.
Yeah, I'll release it today, so they'll get it today, and then they'll have a chance to work on it.
I could do Wednesday.
No, it'll be released today. So either Wednesday or Friday or whatever you want.
Yeah, figure something out.
All right. Okay, sounds good. Thank you.
But one thing that helps me is that when I was in middle school, I studied a little bit of group programming because it was mandatory and I didn't appreciate it. It was terrible, but now I think I should have studied better.
Okay. Do people want to join the group? Should we join the group? All right. So based on what you talked about with the group, what doesn't make sense? Does someone want to say, I didn't understand this, but I understand this now? Or maybe something still doesn't make sense to you and you want to talk about it with the group. So what are your thoughts? What aspect of this doesn't make sense yet that we could talk about? Or maybe it makes sense for everyone. What is your sense?
Can I
Yeah, sure.
Is n equal to the number of realizations of the?
Correct.
Okay, sweet. That's all I wanted to double check then.
Yeah, exactly. So just for those of us who are on the Zoom, this is we're getting draws from a random variable. That random variable, we can have not just one realization from that random process, but we might have multiple realizations, like a coin flip. You have the coin and you flip it one time, and that would be one realization for the random process. Or you could flip it 17 times. That would be 17 realizations. So n is equivalent to the number of coin flips in this context. Very good. Other questions? Is there any aspect of it, no matter how small? Because learning cumulates. Yeah, question?
What, I don't really understand what size is. So when I set size to 100, it gives me a larger number than 0 and 1. So I think we're pulling from anything until like 100 if I set it as size to 100.
Yeah, good question. So the size parameter, we haven't really introduced the binomial distribution, but the basic idea here is that the Bernoulli distribution is equivalent to a binomial distribution with the size parameter set to 1. So we haven't really introduced that. So if it doesn't make sense, that's partly because we haven't really introduced it. But you can think about the binomial distribution as describing the number of successes in a given number of trials. So if we have 100 coin flips, the question could be, how many heads did we get? And if size is 100, now the question is, how many heads did we get when we actually, threw the dice 100 times or threw the coin 100 times, if that makes sense. So when we just have one coin flip, that is also known as defining or characterizing the Bernoulli distribution. So there's binomial and there's Bernoulli, and one is a special case of the other. It's sort of like we have countries, and then the United States is a special case, of the class country. So it's a little bit like that. So does that clarify? Yeah, we'll talk more about that today. Good question, good thoughts. Other thoughts? Is there anything that people want to talk about with this? Okay, so that's that. I won't do this with everything, but let's just flip through this, and if anyone sees anything from last time that doesn't make 100% sense to you, let's talk about it now, because I think it's important to get this foundation. Is anything, looking here, set seed, we did a lot with the binomial distribution last time, or the Bernoulli distribution. We did a little bit with, these logical operations. Do these make sense to anyone? Are there any questions about these sort of operations, which we introduced last time? And Andres, I'm sure we'll talk more about sort of other ways of doing the same things that we did here. Okay. Very, very good. Other questions here? We're almost to the end of this. So we have a little bit more new content, but before we get to the new content, I just want to pause one more time for any questions about any aspect of this, no matter how small. Yeah, good.
What does the number inside the set seed represent? Does it mean anything?
Yeah, good question. So, where is it? So one way in R, this may be, people might know this, but to find a code that has a certain phrase in it, it's just like within Mozilla. You do Control F, and then you can search just like if you were in, a website. So I'm going to search for set.seed, and that'll bring me to where the seed code is. So that's just a little bit of working with RStudio. So the pseudo-random number generators get initialized with a seed. So the basic idea is the random numbers in R, they're not truly random. Instead, they're generated in a pseudo-random process that the intuition for this is sort of like the intuition for how the digits of pi kind of look random. If you look at pi, 3148, whatever it is, if you look like a billion digits down the way, those digits sort of look random, they look uniformly distributed, and this gives you an intuition for how something that's deterministic can kind of generate something that looks random. And this fact is what's used within R to generate random numbers. We want the randomness to be controlled because we want to be able to replicate our work when we have the AJPS or APSR or PSRM paper. We need to be able to reproduce everything exactly. So statisticians and computer scientists have figured out these clever ways of generating numbers that look really random and that pass a lot of randomness evaluation tests, but that aren't truly random. These are pseudo-random numbers, and when we set the seed, this seed here, this number here passed into the seed, that number essentially initializes this random process. So I'm not going to go too much into the details of that, but the basic idea is we're initializing the randomness just in a different way with a different seed, but everything will still be deterministic. So when we initialize it to be 1, 4, 4, 4, we get 46 heads. And then if we added a 4, it's going to be a different number. It's going to be a different number, but it's still going to be reproducible exactly. So the seed essentially controls the pseudo-random number generator. You can sort of think of it like yeah, that's basically what I would say. It controls the random number generation process. Does that make sense? Any follow-ups to that?
So like the number itself doesn't necessarily mean anything, but as long as you are setting the seed to the same integer or number, you are always getting the same results.
Correct. Yeah, the number itself, like this 11444, whatever it is, this number itself has no substantive meaning. It's just a number that we've chosen to initialize the seed. Yeah, exactly. Sometimes you'll see people just set the seed to be 1, because if I set the seed to be some special value, people might wonder, is that suspicious? So in general, it's common practice to set something that, to set a number that has a certain pattern to it. Otherwise, it looks suspicious, I would say. But, it doesn't really matter. And in general, whatever you choose, as long as it stays the same, as long as the seed stays the same, the output of the computation will stay the same too. A good question. Anything else? Yeah.
I'm kind of unclear about the difference between function R binomial and D binomial.
Okay, good question. Does anyone want to answer that question? Anyone in the audience ask the room? Yeah.
Is the R the PDF and the other one the CDF?
You're close.
PMF?
Yeah. So which one do you think is which, based on what you're saying?
Now I really doubt everything I'm saying.
No, let's talk it through.
Okay,
Let's talk it through.
I'm looking at the code.
Okay.
The PMF is the D one.
Yeah.
And then the CDF is the R one.
Close. So the CDF, we haven't really introduced CDFs yet. So if that word doesn't make sense to people, that's okay because we haven't introduced it. But you're totally right about the PMF, the D binom, wherever that is. D, I think it's down here. So remember the D, name of distribution, that is a way for evaluating the density or the probability mass. So you'll see things like D norm and so forth. These are all PDFs, so this is like PDF, this is a PMF, PDF. So when you see D, that means kind of probability density. Just think density, probability density. When you see R, think random number. R means, R stands for random. So D stands for density, whereas R stands for random. So when we use D binom, we're evaluating the probability of seeing a certain thing. So that gives us a number with a precise 100% of the time certainty. So when I say D binom, nothing here is random. Everything is set deterministically based on the structure of the distribution. When I use the R binom, I'm not generating something deterministic. Instead, I'm getting random numbers from that distribution. So you're totally right. It's the D stands for the PMF, whereas the R binom, that is a way for generating random numbers from, or generating draws, or generating realizations from that distribution that you've defined. So those are all the same, different ways of saying the same thing, but that is the difference between the D and the R when we're talking about random number generation or those sorts of things within R. Does that clarify? Any follow-ups? Yes?
So the size, I'm not sure whether I understand correctly. So if we set the size 100 and then n is 1, it means that we flip the coins for 100 times and then we are looking for a sample.
Correct. Yeah. So if we did this, which is what you're suggesting, we're basically, and we'll talk more about this today. So we're introducing this content as we go, but size 100, that means we're flipping the coin 100 times, and n equals 1. So this is a very interesting point because here the random variable here is defined as the sum of these 100 flips of the coin. So we're flipping the coin 100 times, but we're doing that process just one time. So the subtle difference, I'm just going to say one more thing about that. It might seem very similar. In fact, there's a connection between doing that on the one hand, and on the other hand, defining a Bernoulli distribution where you're flipping the coin one time and then summing across those coin flips, if that makes sense. So there's a similar kind of, there's an interconnection between different sorts of binomial distributions together with different kinds of Bernoulli distributions. But in general, you're right. The size refers to the number of coin flips, and the n refers to the number of times you're doing that process. Yeah. If there's a follow-up? Yeah.
I was wondering if you could use the coin flipping example to explain the R binomial and the D binomial.
Yeah, good question. Good question. So we have a coin flipping situation, and our binomial, let's just use size equals 1. So this is a literal coin flip. It's either 0 or it's 1. And we don't know which it's going to be. It could be one, it could be the other. It's sort of like before an election. We don't know whether it's going to be pro or against Brexit. So there's uncertainty about that. And our binomial is a way of kind of flipping the coin and seeing the result. So R stands for random number generator. So our binomial means we're randomly flipping the coin. We're randomly getting realizations for that random process. So that's the R binomial. The D binomial, so let's just try to do D binomial with the exact same parameters as before. If we run it, it's going to give us an error because it's not a way of generating random numbers. D binomial is a way of evaluating probabilities. So we're going to define something more precisely today called the support of the distribution. But the binomial distribution, or the Bernoulli distribution, has support, on, it's either 0 or it's 1. So the support is this set 0, 1. And D binomial is a way for basically saying what is the probability of a 0, what is the probability of a 1. And this is a way for, characterizing the PMF. It basically tells us what is the PMF for, what is the probability of seeing x equals 1, coin flip value 1, in this particular case. So this is no longer random, this is deterministic, and the value of this, or the output of this, is just equal to the probability. So does that make sense? Yeah. So just to put it one more time, D binomial evaluates the PMF, and remember, the PMF, it's defined differently for different inputs. It's a function, so if you give the PMF a 1, it's going to give you an answer that's different than if you give it a 2, and it's going to give you an answer that's different, than if you give infinity. If you give this function infinity, does someone want to say what, or maybe that's kind of tricky. Well, what about 1,000? So what is going to be the output of this? Or maybe you can try and tell me why it is the way it is. So what should this be? This is essentially asking us, what is the probability that x equals 100, where x, is Bernoulli distributed? 0.1. So this is basically what it's saying here. So does someone want to take a crack at what this should be once we execute the code? Or maybe if you do it, what do we get? And why do we get it? So what is the probability that when I flip the coin, it takes on value 100 in this way of quantifying coin flips? What's your sense?
0.
What makes you say that? What are your thoughts? Yeah, good thought. So here, the distribution has a support of 0 or 1. We're going to define that in slides in just a minute. So this distribution only has positive probability either on 0 or on 1. The way that we've quantified this situation is that the coin flip heads quantifies as 1, tails quantifies as 0. So anything other than that is outside of the bounds of possibility. It would be like saying, the probability of the probability of flipping a coin and getting 100 just isn't defined within the distribution. Anything outside of the support of the distribution has probability 0. So in that sense, when we evaluate this distribution at 100, we're asking what is the probability that this random variable takes on the value 100, and this random variable is defined to be, to have non-zero probability only over 0 and 1. So in that sense, the output of this will be 0 because that is not, it's impossible given the structure of the system that we've defined, and the probability of getting a 100 when we flip the coin is 0. So that's just a good way to check your understanding. We can do the same thing with negative numbers. We could also ask, what's the probability of seeing negative 100? And it again would be 0. Yeah, good thoughts. Other follow-ups to this? And this is just one way of saying, if for those of you who do decide to go on to the Stats Masters, one of the things that I would recommend is while working through the conceptual material, about expected values or about this or about that, different distributions, time series, it's always really helpful to set up a little simulation for yourself or for myself to work through things just to see the intuition for it in the computer program, in the code, because it often can be a lot easier than to go back to the equations and say, oh yeah, this equation kind of corresponds to this in the code, and now I have a deeper understanding of it. So that's one thing I recommend if you do decide to go on into different statistics courses, and Andres can answer questions about the master's program if you do have them. Okay, so it looks like there are no follow-ups to this. So now we're going to do some more things. We're going to do some more learning about R, and we're going to be a bit more practical, since some of the problem sets are going to throw you not in the deep end, but in the middle part of the, it's going to be a continuum, and different people will feel different things. But we're going to do some data analysis in the problem set, and I wanted just to give you some sense for doing data analysis in R. And we're going to talk about some things that maybe some of you haven't heard about either. So the first thing is just kind of logistics in terms of how you download packages. So install.packages. This is a function that will download a package which is defined using its name. So you basically say install package gapminder, and this is going to install a specific package for you. Any questions about packages? You can also use GitHub to download packages, but that's a more extended topic for another day. One of the things that is going to be really helpful to you when you're learning about R is just little, what I call tricks of the trade. So I've downloaded this package, but I don't want to have to pull up the PDF to look at the documentation. That's going to cause me headaches. My life is very short. And as a result, one of the ways to basically look through what's in the package without actually looking up the documentation, which is taking away our time, we can just do this double colon, and boom, there's all the functions associated with the package. And I can look, it looks like there are 5 things that this package defines. If you look, there's a little symbol to the left of it. That basically means it's a data set. If you look at other packages, it will look a little bit different. So here, if it looks like this is no longer a data set, this is a function, whereas this means data set. So the different symbols that you see correspond to different things. Like this package has a lot more functions in it and has a few data assets as well, and that's just interesting. Whereas in this case, the gapminder package has only 5 things. So we're going to look at some of those things today. So that's just a cheat, kind of like a cheat sheet thing for you in terms of speeding up your exploration of these packages so that you don't have to waste time or spend more time looking through the documentation. So that's just one thought. Also, notice how there's a nice description to the right of all of these package names, which is super, super convenient for further speeding up the process of figuring out what's in this thing. Okay, so remember, when we did gapminder, questions?
Oh no, I was making a comment how loud that was.
Oh, okay, sounds good. So we have that, and then we can also look at the data set. So remember, we have gapminder, and this is a data set within this package. So this is going to be a data set that we're going to work in. So what I'm going to do now is I'm going to read this data set into my R session by going like this. So now this package has this data asset which is sort of stored within it, so to speak. And now I've slotted that data asset into this object, my data. And I hope the Zoom is still working, but we'll see later on. So we can look at the dimensions of the data object. So dim, that's the way to look at the dimensions. This is really useful. Is my data set, does it have 1 billion observations? If it has 1 billion observations, there are certain things that I will or won't want to do in this whole thing. But if it's a really small data set, then then my options open up. So this is one thing to do. You can also check out the column names. Another another tool of the trade is the following. Just like before, when I looked at the functions that were in that package, now I can look at all of the columns in the data set, and I can get a little a window into them by $, and then there's the column names, and I can kind of move through them and look at them and peruse them, and I can see what values the different things take on, the different entries take on. This is a way for me to peek into the data set without actually having to do, without actually having to view it. You can view the data set by doing view data. This is something that will just give you the whole data set. This looks more like almost like Excel. Some of you may have used Excel or Google Sheets. This looks a little bit like that. But whereas in Google Sheets, I could go and type, and change these numbers. I can't just change these numbers in this viewing process here. The idea is if I just would go and change these numbers in this, in this data set, that would be not reproducible. I want everything to be reproducible via scripting. So in R, we're not going to just change, this 1977 to 1978. We're not just going to change it. We're going to do everything in this scripting language, which will be automatically recreating everything. Once we load the data set in and run the code again, we'll get the same result, as opposed to this complex process of, tweaking the data manually. That's just too complex. So we're actually going to do it all through the scripting. Are there questions about this? Are there comments? Are there thoughts?
Is there a reason that the V has to be capitalized?
Good question. So the answer is yes. So if we I'm pretty sure the answer is yes. Let's see. Yeah, so it just turns out that certain functions have been defined in certain ways. And in this case, view is a function that's been defined with a capital V. We'll talk more about this in a minute. There's actually a way you could change that, but in general, so think about R. It's one of the reasons why people like it is that it has a lot of pre-built functions for you to use. Functions like view. It's not like C++ where you'd have to code all this up yourself potentially. Instead, it's nice because it has a lot of these pre-built functions so that you can plug and play much more quickly, as opposed to loading in libraries and loading in this and loading in that. There are a lot of base functions that are from what's called base R, and view is one of those base functions. Good question. Okay, so now we're going to, and some of this may be new to you, some of this may be old to you, but it's never a bad idea to review. So we're going to do some reviewing. We're going to subset the data. So remember, we have, some of you might remember generating logical statements. So one way that you can access the column elements so what's the class of this? The class of this is basically a data frame. So one way that you can access the columns of a data frame is by going like this. You can also go like country. You can also go like this. These two things generally will work. There may be reasons to do one versus the other, but that's not really important for now. What is important is that once you've accessed this column, that basically, so you have this data set, and I'm writing on the board for those of you who are on the YouTube, and we've accessed the column. That column has the same number of entries as rows in the data set. So what we can do after we've accessed that column is we can basically ask ourselves, when are the entries in this column equal to Afghanistan? So this is what we're doing here. And Andres will show some different ways of doing this using the tidyverse. We're just using elementary logical operations to get some practice doing that, in addition to showing you other ways of doing things. So what we're doing here is we're setting up a bunch of trues and falses, and things are true when country equals Afghanistan, and then we see a false when the country value is not equal to Afghanistan. So if we just look at country again, it looks like this. It starts off with Afghanistan, and then it goes on to other countries. And when we do this calculation here, we see that we have a bunch of falses, but the first entries are trues, and so forth and so on. So this is a series of logical operations. And in R, you can subset data using those logical operations. So if you basically have this life expectancy column, you can subset the life expectancy column, and then those trues and falses subset the life expectancy column on the basis of those logical statements that we just have. it's going to return all of the values where the that logical operation or that logical output was true, and it's only going to return those. So this is a way of subsetting your data to look at just the life expectancy data for Afghanistan. Is there any questions about that? Okay, we can do the same exact thing, but now subset the rows. A matrix, a data set in R has rows generally, and it has columns. We can subset rows by having a condition on like this. So this subsets rows, and then if we put that condition not on the left-hand side of that comma, but on the right-hand side of that comma, this subsets columns. And we could subset both rows and columns simultaneously by going like this, subsets rows plus rows. So this would subset both. So there are just different ways of subsetting your data. The first, think of it like rows, columns. So it's first is rows, then is columns in this notation of subsetting. Are there questions about that? So that we're going to use that principle here to subset the rows of this data frame. So this data frame is a data object, and we want to subset the rows. So we've put a condition here and then a comma. The condition, comma, that indicates we're going to subset the rows. If it was comma condition, that would subset the columns. But we're going to subset the rows. And we see here that this we're going to run the code, and it gives us something. We can do some tests, like what is the class of this thing? We had a data frame before, but what do we have now? Well, when we subset the rows of a data frame, we get a new data frame, but this new data frame now has different dimensions. Remember, DIM, that stands for dimensions. And now this is 12 by 6. So that means we have 6 entries of data for Afghanistan. 6 entries. No more, no less. Okay, questions, comments? So this is how we subset the rows. We can also use the which command. So which basically, I'm just telling you different ways of doing the same thing. So which instead, so we have these trues and these falses. And does someone want to take a stab at what which seems to be doing? So here are all the trues and falses. So it's like false, it's true, 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 and then it's false, 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 false. What do you think based on this and seeing the output of this, what does the which seem to be doing here? Does anyone want to take a stab at it? Wild guesses are totally fine. What is which doing? Yeah.
It's going through the country column, and it's looking for, if this value is Afghanistan, then it's true. And then it keeps going through it until it's finished with the column. That's why the first part is all trues, because Afghanistan is the beginning of the alphabet, and that's why it ends with a bunch of falses, because it's done.
True. Good. No. Very good. Very good. That makes sense. And then the which, someone wants, that's what this is doing here. And then what's the which doing on top of that? Well, what the which is doing on top of that is basically it's saying we have those trues at the beginning, and which returns the indices of where there's a true value. So that's why we have 12, 1 through 12. That basically means this is equivalent. If we have which true, 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 false, this will return 1, 2, 3, because the 1, 2, 3 element is true and everything else is false. So it's just going to return the trues. So I bring this up just because in some cases, if you have an NA, the logical operations can sometimes cause problems. So for example, if you have true, true, NA, false, and we want to subset 1 through 4, if we have something that looks like this, the NA can sometimes cause problems. So we get something that looks like this, where the NA slots in, and it returns NA in that position. So it gets a little bit confusing. So if we wanted to remove that possibility, we would just have this which command applied over it. This is a bit more advanced, but this for those of you who want to get a motivation for why we're doing this. The logicals sometimes don't deal with NAs well, where the which generally will you deal with the NAs pretty well. So that's a bit more advanced for those of you who are interested in it. It's not super essential for now, but just know there are different ways of subsetting data. We've gone through a few of them here. Andres will have still other options for different settings and so forth and so on. Okay. Are there questions about that? Are there comments? Okay. Now we're gonna do 3 more things in this R session, and then we'll take a break, and then we'll come back to the conceptual material. We're going to do some plotting, and then we're going to introduce functions in following up with what Andres, I'm sure, covered as well. And then we're going to introduce you to for loops just so that you see it, and then we'll talk more about them later on, because this is going to be really important for doing your analyses. Sometimes the reviewers might ask you to redo your analysis with these conditions and with these conditions and with these conditions, and instead of retyping everything up to have thousands of lines of code, you can more succinctly write what's called a for loop to what's known as iterate over those conditions. And we'll talk about what that means in a minute. But that's just motivation for what we'll do. So first, we'll just do plots. So this is just and I'm sure Andres covered this as well, but the plot function in R just makes plots. Plots are really important. When's the last time you read a paper without a plot? Every paper has a plot, pretty much. And if it doesn't, it's probably a political philosophy paper. And I don't think many of us here are political philosophers. So plot is just a plotting command. And the basic, if we wanted to learn more about the syntax, we would either go to ChatGPT or we could do plot, and we could learn more about it. So plot takes an X and a Y argument, and then this ellipsis ... that basically says there are all these other arguments that you could apply to this or that you could use, but we're just going to focus on the first two right now. We have this X and then we have this Y. Notice how you don't so this plots it. We have the X and we have the Y. This is all the data for Afghanistan. This is the year on the X-axis, and this is life expectancy on the Y-axis. So we have an X-axis and we have a Y-axis, year against the life expectancy. So as you can see, this life expectancy is really low. This is 30 going up to 40. So this is a low life expectancy. But a few things to note. You don't need to put in the X and Y, but you can, and it's often much clearer to. In functions, there are things known as positional arguments. So when we define the plot function, basically the function is going to assume that the first thing is X, and it's going to assume that the first thing is Y. So based on the position of the argument, an assumption is going to be made about what that argument is. This is known as a positional argument, and it's useful in various other programming languages too. But it's often good practice, and I generally like to say what is the argument that I'm defining, because sometimes the positions might change or I might be confused, and in general it's best to be explicit. What is X, what is Y? And here we have X and we have Y, and we've plotted year on the X-axis, with on the Y-axis life expectancy. So this is just the base plotting technique. Are there questions? Are there comments? All right, so now there are all sorts of variations to this. Some people like ggplot or other things for plotting. I personally don't really have a preference for what you use. There are some principles to visualization that we'll talk a little bit about in the class. But there are ways to change the margins of the figure. And then what we've done here is we've added an X label and we've added a Y label. And we've also changed the margins. These numbers, like when this mar equals 5511, 5511, this is us changing the margins. In general, like whether this should be a 3 or a 2, that's just going to be something you play around with. You try a 1 and it looks bad, so then you try a 4 and it looks better. Then you try a 5 and it looks even better. So these numbers are just things that you'll play around with through practice, trial and error for those parameters. So this is us labeling the plot, giving us an X-axis, giving us a Y-axis label. Otherwise, things are exactly the same as before. So what we're doing now is we're taking a base code and we're just iterating on it and showing you all the options and showing you what you can do, because in your papers, your research papers, you're going to be doing a lot of plotting, and you're going to want to make this as looking nice as possible. So you can also change other things about it. So we've made a plot that goes crazy with formatting. We change the dots. I've listed out here all the different explanations for what the different options are. But think about it like going to you go to the suitcase. Well, maybe this is a bad analogy, but you need a new suitcase. You go to the suitcase maker and you say, I want a suitcase that has these parameters, that has that has silver trim and all these different parameters. These are what these options are. We're basically specifying all these options to this function, and we're going to show you later on how to write a function. But this is the basic idea behind the plotting function. We're plotting all these different things, and we're giving it all these different options so that our plot looks nice. And in this case, we have just these different parameters, and I've laid them out here. Are there any questions about this? It's similar to what we did before, but we're just adding options to it so that it looks just like how we want it, because we want it to look as nice as it can be so that we can convey our ideas as compellingly as possible. Don't underestimate the power of a plot. Plots generally are some of the first things that your readers will look at. So if your plots don't look super nice, super professional, super compelling, your audience might be, they might be unsatisfied. So just keep in mind the power of plots. And we'll, in the problem sets, give you practice making plots and so forth. But I wanted to introduce some options with this. Any questions about that? Anything that doesn't make sense? Any things that you want to talk through? Yes. Yeah, good question. So the which function. So we have all these trues and falses. Does that part make sense? Does this part highlighted? Okay. So that part makes sense. So we have all these trues and falses, and there are multiple ways to subset data in R. One way is through these trues and falses, which it selects all of the data set elements where the condition is true. But there's another way to subset data too. That second way uses indices. And indices are important for things we'll talk about later on, like with the bootstrap, which some of you may have heard about. But the basic idea here is that this which command, it returns the locations of all of the trues. So for example, if we changed Afghanistan to, let's say, United States, now the indices are different because the location of all of the trues associated with this US condition those locations are different. So the US is at the end of the data set just based on how it's ordered based on alphabetical order. So this is what you'll get here. So just maybe even a simpler, clearer example would be which, true, false, false. Do you want to take a crack at explaining what the output of this will be? So we have which, and then we have these trues and falses. What do you think this will return when I hit enter? Yeah, exactly. Because the first element is a true, and the third element is a true, and those are the only true things, and those indices are what I can also use to subset the data, because I don't want to use, you're downloading the L2 voter file, and it's like, terabytes of data, but you just want data from, let's say, Pennsylvania, because your study is in Pennsylvania. So subsetting data, very important, and it's going to be useful, and these are some of the tools, some of the techniques for doing that. Good question. Other questions, other things that people want to talk about? Alrighty, so this is this. We're going to go crazy with plots in a minute. In a few minutes, we're going to actually make 176 plots all at once, and we're going to show you how to do that. But before we do that, we have about 10 minutes before we go into like a mental reset break time, and then we'll come back. But before we do that, I want to talk about two things that are important, and it's like when you're learning how to ski. You learn how to ski on the first day, and then you go back to the slopes the second day, and you kind of review things, and you rehash things, and then you keep rehashing things every time you go out. So we're going to review these things, on a continual basis. But we'll talk about functions. A function, what is a function? Well, a function is something that you can define in R, and basically they're going to take in an input, and they're going to do something to it. Not all functions need an input. So for example, I could write a function that looks like this. Or maybe R binom is better. R binom 10 size equals 1, prop equals 0.5. I could write a function without any inputs. This function is just going to, it's going to do whatever it's going to do regardless of whatever input it gets. So, but in general, a function will have an input, and in R, you basically write a function like this. So you name the function, identity function, and you're going to name it, and then you're going to say function. So this basically tells R we're defining a function, and then we're going to list the input to that function, and then we're going to say here in the brackets what you do with the function, or like what you're doing, what computation you're performing. So this is the identity function that we've just written. So does someone want to take a guess? Like what happens when we apply the identity function to the input 1000? Yeah.
It's the return 1000.
Yeah, and what makes you say that?
Because the function takes x and it's it returns x. So basically, it will return what it will return inputs.
Exactly. We're not doing any transformations. We're not doing any sines or cosines. We just have the input and we return it as the output. So this is one way to write the identity function. What do you think will happen when we give it apple? Yeah, it'll be the same thing. So now we're going to do some things different. So this is going to be useful later on, but also now we're going to define another function, just x squared. So we're going to take x as the input, and now we're going to square it. And now what happens? Let's do a number like 2. What happens when we put in 2?
4.
Yeah, exactly. 4. What about when we put in apple? Yeah, we'll return an error. So in R, it'll get an error. For those of you who are into the computer science, in some computer programming language, well, I don't need to go into those details. It's not important for them. But just know that the class of the input is important for what kind of transformations you can apply to it. So this is an important concept. So the class of apple is character. The class of 100 or whatever it is, 10 or 2, this is numeric. And the square function or the square operation can only be applied to some input. So remember, this gets back to the theory of data types, the theory of kind of type theory, type dynamics. Okay, so that's that. So when you're writing your functions, you can have multiple inputs, and you can also have default values. So here on line 1, whatever it is, 82 in my version, we have 3 inputs, A, B, and C. And notice how C, I've defined it to have, C equals 2. You might ask, what is that doing? Well, that is essentially setting a default value. Sometimes you might want to have a default value. I want my default to look like this. My default plot size to be 7. Or my default value of C to be 2. And then you do a calculation, A times B times C, and then that returns a value. And then you return that value here. Return basically means return this as the output of the function. Return means return this as the output. Technically, you don't need it, but in general, it's good to explicitly state what is my function returning, and that's what return is. It returns to me this. So a return, where is it? There it is. Okay, multi-input function. So now because we have a default value for C, I don't need to say C is X or C is, I don't need to say C is 3 or C is 5. If I don't say what C is, it's going to assume the default. This is really important if you're writing functions that other people are going to use. In general, it's good to set defaults because people will just use the defaults. And if you don't set a default, they might choose a really bad default, and that might cause problems. So in general, it's good to set a reasonable default if you do need a default. So here, we're taking A equals 2, B equals 1, and then C as the default 2. We're multiplying them all together, and we're getting 4. This is what we're getting there. We don't need to use the default. We could say, C is 1, and then we're going to get a different answer. But this is important for setting defaults. Sometimes you might want a default, sometimes you might not. But this also illustrates how you might have a function with multiple arguments. Notice how we could use the positionality of the arguments to compute the final answer. So I didn't say A equals 2 or B equals 3. I just used the position of the argument instead of explicitly saying what things were. But this in general is much more confusing. People get confused. It's better to say what the arguments are and so forth and so on. So this is just giving you experience with functions. Are there any questions at all about functions? This is going to be important because a lot of what you're doing in your research is doing the same thing many, many times. And if you think of a function like a template, or what's a good analogy?
A recipe.
Yeah, it's like a recipe. You don't want to have to rethink in your mind what is the formula for OLS or what is the way of getting standard errors from cluster standard errors. I don't want to have to retype it up every time. Instead, I want to basically have the recipe that I get out of my recipe book and I just let my computer follow the recipe exactly. This is an analogy for functions. And I'm going to show you in a minute how you can use functions to plot the economic trajectory or the life expectancy trajectory for every single country in the entire world. Instead of typing, plot 156 times or whatever it is, I'm going to write a function and I'm going to call that function over the countries, and this is going to be just giving you illustration for how you can use functions to automate your process. Think of a function as a tool to automate what you're doing, and automation makes your life easy. So we want to make your life as easy as possible. Since life is short, as we mentioned, and we need to really get through this as quickly as possible. So I've written a plotting function. Let me know if you have questions about it. So it takes as an input a string country, and then it subsets the data on the basis of that, and then it plots the data on the basis of that. And the only new thing here is main. This defines the figure label, like on the top of the figure. There's the top label, and then there's X and the Y axes. In general, well, that's not important. So we're going to define this function. We've defined the function, and we want to kind of see what things can we input to it. So here's all the data that we have. We have 12 observations from Venezuela, 12 from Vietnam. Looks like we have 12 observations from most countries, and these are all the list of countries within the pool. So now we're just going to try out the function. Instead of having to rewrite everything, retype everything, now I just call my function, and like magic, it spits out the answer without me having to think. It's automating the process. So, United States, this is the trajectory from the US. This is the trajectory from Zambia, some interesting things that happened in the 1990s. This is the trajectory from China. In other countries, we can do as well. So this is a way to make your life easier by giving you access to this notion of function, giving you insight into this notion of function. Okay, so I know we're getting to the time where we're going to have a mental reset. But I wanted to just introduce you to the notion of a loop, because next time we'll introduce it more formally. So let's say we wanted to plot not just one country, not just two countries, but every single country, and we wanted to plot every country in under 10 lines of code. You might think I have 100 countries, I need at least 100 lines of code. But the answer is no. The answer is you can do it in far fewer lines of code using what's known as a loop. And I'm going to do it. I'm going to just hit enter, and you'll see what it's doing. I think based on what you're seeing here, we're seeing every country, the trajectory of every country, and you're getting an intuition for what a loop is doing. We're basically iterating through every country in our data set, and we're performing that function with that data input varying as we iterate. So every country, we're iterating over it, and we're putting every country's name into this plot function, and we're just iterating through all the countries that we have, and this is what we're seeing. And we've added a little bit of system sleep so that we could pause the function, pause the loop so that we could see what's happening. But the basic idea is that a loop is going to iterate through something, through what's called a set. And in this case, the set that it's iterating through is the set of all countries. And within each cycle, we're going to do something. And what we're doing in this case is we're going to just plot the country trajectories, but the basic idea is a loop is just an iterative process for performing a computation, and the function makes our life easier in terms of using a recipe. So these are just a few insights. Before we conclude this part, are there any questions specifically about this? And we'll talk more about this next time. So I just wanted to start talking about it so that it's in your mind for next time. But are there any questions? Are there any thoughts, things that aren't clear? Or we could talk after class too. Yeah.
In the plot function that you defined, there's a line saying par, P-A-R, bracket M-A-R. I don't get the part.
Yeah, good question. So the question is, what is this doing? I guess we have it up here too. So par's up here. Par. If you hit question mark, it's going to set graphical parameters. So ggplot uses a different technique. We're just using base R now to introduce everyone to it. But the basic idea is that there are certain things. We have our plot, but then we have all kind of the meta parameters of the plot. So we have things like what do the figure margins look like? So if we changed mar, now notice how the margins are changed. Like the space on the top and the space on the left-hand side have now encroached upon the figure. So this par, it's basically saying we have these graphical parameters. Par defines graphical parameters, and now we're going to reset the mar, standing for margin part of it, so that the margins look one way or look the other way. So I could, make the margins look much smaller by going 0. These, this refers to, I think, inches or centimeters or something. How should the margins look now? Those margins have gone away. So this is something that takes some getting used to, and I don't expect you to kind of from day one know all the ins and outs of this, but the basic idea is there are a various number of graphical parameters that you can read more about here. Those graphical parameters, think of them like the hyperparameters for your plot. And those hyperparameters are set by calling this. And another example of a hyperparameter would be like the number of rows and the number of columns. Let's say you want to do a 2 by 2 plot or a 2 by 1 plot in terms of rows and columns. You could potentially do those sorts of plot arrangements using the par function, setting the graphical hyperparameters. So this explains what par is, and this explains what mar is. Any follow-ups to that? Okay. Any other questions? Any other thoughts? Alrighty, so let's take a 4 or so minute break. We'll try to come back at 1:56. Hang tight if you're on the Zoom. We'll come back together in about 4 minutes. Yeah, good question. So notice how the trues and falses, they're not concatenated together to form one long vector. So this which command basically sees the first element, and it will, and then it'll try to perform, its task on that first element. But then it sees a second element and third element and fourth element, and it gets confused. So in other words, the which function has one input, but you're giving it 4 inputs. What we need to do is we need to combine them together, and you can combine them together by going, C standing for concatenate.
Okay, so I put all of this here.
Yes, exactly, yeah.
And then in which I still keep it this one.
Yeah, so just so if you just do on line 131 which to that particular part, it'll give you numbers, I think.
Which,
Yeah, so for line 131, if you apply which to that whole thing, yeah. In other words, which takes in only, it has one argument, and that argument is going to be what's called a vector. So we need to combine all the trues and falses to form a vector. Yeah. Thank you.
Yeah, you could probably reserve room.
Yeah, I worked out on
Any follow-ups to that? Or?
It's uphill to bats from Blueberry.
Yeah.
You could just, if there's like a sky bridge from here to the coast,
That's good.
which is right next to
Yeah. Oh, yeah. Oh, yeah.
I saw it this morning, or like on my way here, and I was like, interesting. I'll go back that way and see where it's missing out.
So trial by fire.
I mean, that's how I learned how to navigate. Sometimes I'll just like navigate somewhere and I'm like, okay, I have to figure out how to get home from here by myself. And I'll like Google Maps.
Same, my girlfriend
That's how I learned.
I have my
Very
good.
anxiety just won't.
Yeah, I think it's good to
Well, you can always pull it
kind
back
of
up.
show it again, and then
I basically know my way home.
add on.
It's how my brain makes
Very good.
connections. So like, okay, I'm here.
Ooh, I'm gonna
Street is
pull up
here,
the next
this is
material.
For some reason, 35 is here.
Sounds like there was.
Cool.
Let me check. But I don't have a key yet.
My friends at U Michigan and a parent, this hasn't been officially stated, but someone was like hacking their system this weekend, and so the school removed their network from the internet, and so there's no one on campus that's on that right now. I just got a text from her, and she said, oh, my machine, she does like natural science, and she's always like cancer numbers, and she's like, all of my machines are offline. And then she goes, why do they have to be online? They shouldn't need to be online. Like, they have like outputs on the screen.
Okay, let's get started, and we'll go from there. We'll see how far we can get. For those of you who are on the Zoom, last time we covered probability theory, like motivating it. Why do we do probability theory? And we had a few different answers. One answer being probability theory is a way to explain the uncertainty that we see in the world, but it's also a way to kind of define what we mean by averages and define what we mean by uncertainties, in addition to how we can use probability theory to combine information from different sources through things like Bayes' rule, which we'll talk a little bit about. So this was motivation that we talked about last time. And then we also talked a bit about just some fundamentals of probability theory. We talked about how there are certain elementary players, almost like in the Odyssey. You have certain characters who recur and there are relationships between them. It's the same thing here, where we have certain characters, which certain definitions, certain kinds of things, and we have relationships between them. Things like random variables, things like PMFs, and so on and so forth. So we talked about that, and so forth and so on. If you are on the Zoom or on the YouTube, definitely come and talk to us if you have questions, if you have comments. Since some of this material I know will have been missed through the last Zoom, which had the corruption with the file. So that's I'm just reviewing some of that. And today we're going to talk a little bit about just some more details. I don't think it's good to try to move too quickly early on. I think it's good to get a good foundation and then to build up our understanding and build up our confidence in the material and then move on from there. So we talked a little bit about PMFs last time, and we talked about some probability rules last time. In the roughly 30 minutes we have together today, I want to talk a little bit about named PMFs, and then talk a little bit about PDFs, and then we'll go on from there, and we'll see how far we get. So we've been talking about things like a Bernoulli distribution. Well, what do we mean by that? What exactly does that mean? Well, it turns out that there are certain kinds of distributions that are named. So what do we mean by that? Let's break it down very simply. So a distribution, it characterizes the uncertainty over some kind of random variable, and there are certain kinds of uncertainty structures that just recur again and again. One of those uncertainty structures would be the structure of a coin flip. It just so happens that in many situations we can model the world in terms of binary outcomes. Either someone voted for a Democrat or a Republican. It's useful in some situations to model things like that. It could be that there are other candidates too that people voted for, but we abstract away from those details and focus only on, let's say, two-party vote choice. So the support of the distribution is going to be important. So every distribution has a support. A support defines the set of possible values that the random variable can take on. So for the Bernoulli distribution, the support is 0, 1. In other words, this distribution is defined to have non-zero probability over 0 and over 1. So this gives you some sense for what we mean by a named distribution. So another way of thinking about this is in terms of the variety of supports that we can work with. So in some situations, we might not just be interested in is it a yes or is it a no, but we might be interested in the total count of things happening. So for example, some of you study Civil War, some of you study the number of protest events. That's not a binary yes or no. The number of protest events is a count variable. So remember, it's almost going back to that issue of data types. You can almost think of the support of a distribution as being defined over a specific data type. Like, is this distribution defined over integers, like counts of things, or is this defined over all numbers between 0 and some upper value, or is this defined over just 0 and 1? And the thing that the distribution is defined over is known as the support. You can think of it like the support for a house. The distribution is like the house, and the support is like the values that it can take on, kind of like the structure of the house. So that's one analogy for you. So just to give you some examples here, we'll talk more about these as we go. And it's almost like you'll get to know them through the course of the semester just by familiarity, maybe with the problem sets, maybe with the examples from class. But there are several different kinds of random variables that are named, and they're named because they work well over a specific support. So one kind of random variable might be defined over binary values. That's like the Bernoulli that we've been talking about. Another kind of random variable might be defined by taking on any one of k values. So it could be a 1, it could be a 2, it could be 3, all the way up to a k. That would define another kind of distribution known as the categorical distribution. There are other supports, for example, the positive integers. So in the context of conflict studies, we might be interested in modeling count events. In that case, the support of the distribution is any positive integer. So there could be 0, there could be 1, there could be 2. There's no upper bound. There's a count, and the distribution is defined over any value from 0 to positive infinity along the integer. So this can be modeled according to multiple distributions. So, for example, the Poisson distribution, which we'll talk a little bit about, or the geometric distribution, which we'll talk a little bit about, they all are defined over the same support. So you might ask yourself, why is that, or what are the implications of that? Well, one of the implications is multiple distributions can be defined over the same support. So you could have, let's say, any kind of real number. There are a whole number of distributions, named distributions, that are defined over that single support. In other words, those different distributions will imply different assumptions. Those different distributions will imply different dynamics. So for example, is this distribution, does it place more value on extreme events or less value on extreme events? Those are all characteristics of the distribution, and that would motivate why in some situations you might want to model the data using one distribution. In other situations, you might want to model the data in another way. So for example, in the Poisson distribution, there are certain assumptions made about the variance and the mean and how those two are connected. But if you wanted to make different assumptions, you might make a different distributional choice. So the key insight here is that there are certain named distributions, and they're named because they commonly are used to describe the uncertainty over certain kinds of random variables, where those random variables have a certain property with respect to the support that those values can take on. So in other words, is it binary? Is it defined over any number between 0 and k or 1 and k? Is it a positive integer? That's the support, and then the uncertainty quantification comes in through the distribution. So is it a binomial, or is it Poisson or geometric or whatever it is, defines the exact structure for the uncertainty over the random variable. So this is one way of trying to give you some insight into this. There are big sheets of distribution, so there are thousands of distributions, and there are sheets of distributions that go over what things look like at that level. Let's just maybe show you one of them now. So if we just go to this and we go to wikipedia.com. Well, I guess my internet's off, so I'll turn that on quick. But the key insight is that they're just different distributions. And actually, let's go to Piazza. They're different distributions, and they all have a different formula. We're going to look at one of the, in a sense, formulas in a minute. The formula of the distribution basically it's a way of computing the probability. So you give the distribution a value, and it cranks and turns the levers, and it spits out a probability through that. So if we go to resources, and if we go down to probability cheat sheet, we have something that looks like this. And I think at the bottom of this, we have a listing of distributions. These are all named distributions, meaning they're more common, meaning they're commonly used to define certain things. So we see the name of the distribution, we see the PDF/PMF, and then the support of the distribution. So remember, support is the values that this distribution can take on with non-zero probability. So the support, for example, for the Bernoulli is 0, 1. The support for the binomial is any value between 0 and n in this particular way of framing the distribution. In each distribution has certain properties, and those properties are things that we'll talk about. I haven't told you how to compute them, but there are things like expected values and things like variance and things like moment generating function, which isn't super important for now. But the basic idea is that the PDF or the PMF, this is often derived using various stories or various tools or principles, and then from the PDF or PMF, the expected value and the variance and all these other things flow. So if you think about it in terms of a chain of events, the PMF or the PDF that gives rise to the characteristics of the distribution, the characteristics like the mean, the characteristics like the variance, the other characteristics as well. So the PDF or PMF, or later on we'll talk about CDF, these are kind of like the elementary building blocks of the distribution that tell you a lot of the things that you need to know about it. So this is just me showing you all the different distributions that we see here. There are more. This is just a small snapshot, but this is just one way of giving you a sense for all of the named distributions that might be relevant, and we'll get to know some of them well, and so forth and so on. So are there questions about this named distributions, what they're doing, why we might care, other aspects? Okay. So I think we have about 20 or so minutes. And then, so this was a bit about named PMFs. And now let's just talk a little bit through an example, since I know people like examples. And through the problems that you'll get more examples, through some of the readings that we'll update, we'll give some examples as well. But one of the distributions that people sometimes talk about is the Poisson distribution. And distributions have a certain kind of narrative or story associated with them about when the distribution applies, best. And the Poisson distribution applies best if we have a certain, if we can think about a random process where within a specific unit of time, an event happens with a certain frequency. So for example, if we're thinking about protest events, if we can, in an abstract way, think of a protest having a certain baseline rate of occurring, if we think about that sort of as an abstract process, and if we then assume something about how different time intervals are independent from one another, then it turns out that the number of protest events in a specific length of time have a specific distribution associated with them, and that specific distribution here can be defined using can be characterized using the Poisson distribution. So I've just defined a Poisson process. The details aren't super important now, but the thing that is important to know is that under certain assumptions, a specific kind of random process will take on a specific distribution. So under these assumptions outlined here, a given random variable takes on the Poisson distribution, which has a PMF that looks like this. So PMF here, the PMF is a little bit uglier than what we saw before. I haven't derived this for you, so this is kind of coming out from the sky as if from nowhere. So don't feel bad if you don't explain why it is the way it is, because I haven't told you why it is the way it is. But you see a lambda here, you see an x here, you see a factorial here. Let me just explain a few things, because we'll come back to it in a few minutes. So the left-hand side, px equals x. This is something that we've seen before. This is something that hopefully people are starting to become familiar with. Remember, capital X is the random variable, and then little x is the specific realization of the random variable. And we're basically saying the probability that this random variable takes on the specific value x could be 0, it could be 1, it could be 2, it's a placeholder, that this quantity here on the left-hand side is equal to the quantity on the right-hand side. Okay, any questions about that? About the left-hand side, reviewing the left-hand side? To really understand the intuition for the left-hand side, it takes some time because, random variables are not always intuitive to people, so it takes time. But if there are any questions, we can talk about them now. Then we have this equal sign, and then we have this thing on the right-hand side. And I want you to note a few things. First of all, we see that little x appears on the right-hand side. But we also see something else. We see something else, this lambda. And we can ask ourselves, what is this lambda doing? It seems to just come from the sky. Lambda is a parameter of the distribution. Remember, before we had, in the Bernoulli case, we had a coin flip. And there was that probability of a heads or probability of a tail. We called that probability P. For those of you on the YouTube, I just wrote P on the board. So P was the parameter. And that, in some cases, might be set to be 0.5 or whatever it would be. Later on in the class, we're going to try to think of computational ways to figure out a better guesstimate for what that P should be given data that we have. But we're not talking about that now. What we are talking about now is just what conceptually is this lambda, what conceptually is this P. These are parameters that define the structure of the randomness within the distribution. So in the case of the Bernoulli distribution, we have a 0 here, we have a 1 here, and depending on the value of that parameter, either the histogram of events from this random distribution would look like this, or would look more like this. Like, is which of the two is heads or tails going to be more likely? Well, that is going to be determined by the probability of heads. That's intuitive. That makes sense. But P is just a parameter that controls the distribution. And in the same way here, we have the left-hand side, and lambda now on the right-hand side is just another parameter that controls the randomness present within the distribution. So if lambda is bigger or if lambda is smaller, the number that we get when we perform this calculation is going to either be bigger or is going to be smaller as well. So lambda is what's known as a parameter that characterizes the distribution. So the distribution, it basically it needs a parameter to tell it how it should look, how it should be shaped. And lambda in this case is one of those parameters. In the other case of these other distributions that I'm showing you on the board here, we have other parameters. So the parameters are kind of, we can go through different distributions and look at different parameters, but different distributions will have different parameters and also different numbers of parameters, and that might be important later on in the statistical modeling part of the course. So we won't forget about that. But this is just an example of a distribution that looks a little bit different. I've given you some intuition for this. There are some assumptions that go into this distribution. We'll talk more about it later on. This is just giving you another example of a PMF where things look a little bit more complicated. And it's also giving you an example of, what is a parameter? Well, a parameter is just it's not a random variable. So there will be a lot of nuances later on in the class, but the parameter is not a random variable. Your estimate for that parameter might be a random variable, but the parameter itself here is not a random variable. And the basic idea is it defines how the distribution looks in terms of what's more likely and what's less likely. So that's what we have there. Are there questions? Are there comments? Are there points of confusion? Does that make sense to people? And it's totally fine if it doesn't. If it doesn't make sense, that's actually good, because that means we can learn together. Whatever's confusing now won't be confusing if we talk it through. So let me know if there are any things that are not clear. So this is just an example. This here on the bottom is a visual example for how this distribution changes when we change the value of lambda. When lambda equals 1, there's more probability mass around events that are, So here on the bottom, it's px equals k. That's different notation than what we've used. In our notation, it would be px equals little x. So you'll see different notation out there, but in this case, replace k with little x, and everything will make sense in that sense. But as we change lambda, we see that the distribution looks different. What that means, distribution looks different. What that means is that certain realizations of this random process are more or less likely. So for example, when lambda equals 10, that means 10 protests per whatever month, for example, is the most likely value. But when lambda is 4, now 4 protest events per month is most likely. So the lambda, it controls the contours, the shape of the random process, so to speak. So this is one illustration, visualization of the Poisson distribution, which is another distribution defined over discrete events, which will be important in a minute. That word discrete. Are there questions about this before I move on? Like I said, don't think that you need to know the derivation for this. We might do that later on, but right now just know that given that we had this PMF, how could we think about it? And I've just told you a little bit about how we would think about it in that case. Okay, so here I've listed, I'm not going to go through them, but I've listed out the stories of other discrete distributions. Discrete means that the support is not continuous. So we have Bernoulli, which we've talked about. We have here sort of a story motivating what characterizes that distribution. Then we have an application. We also have the binomial distribution, which we've already talked about as well, and it's just listed out in a different way. We also have a geometric distribution and a hypergeometric. These aren't, they're not all equally important. Some are more important than others, but just know there are multiple distributions defined over this what's called discrete, domain or support. And this is just giving you some intuition for when certain kinds of distributions would be more, or certain kinds would be less appropriate for your problem. Question?
What are we requesting for?
Good question. So support meaning the different, so we have a distribution, and the question is, where is that distribution defined with non-zero probability? So we have, basically support is the values that random variable can take on. So so ultimately the support is a set. Remember back to sets, Andres was talking about sets. The support is a set. That set could be either 0 or 1. That's what the support of the Bernoulli distribution would be. Or that set might be the set of all positive integers. That's what the Poisson support would be. Or it might be something else. So support means the set of values that a specific random variable could take on. Yeah, good question. Other questions, other comments, other thoughts? Okay, so we have about 10 or so minutes, and if there are no other questions, I'll move on to the next part, which is basically just doing what we just did, but now generalizing it, or doing what we just did, but now in a new space. What we were talking about before was in the space of discrete possibilities. The random variable would take on, either a 6 or a 7 or an 8 or a 1 or 2, but there was a discrete set of possibilities. But in other situations, our data might not be best modeled by a discrete set. For example, income isn't best modeled using, a discrete set of incomes, iterating by pennies. We think about income as a continuous sort of thing. It makes sense to, think about the income as a continuous variable. So whereas the PMFs were defined for discrete random variables, PDFs are defined for continuous random variables. There are some mathematical details, and I have it listed out here for those of you who are interested. It's not super important. The important thing is just that the PMF is defined over discrete things. The PDF is defined for continuous things. And what those words mean can be a little bit subtle sometimes, but I think we all have an intuitive understanding of what's continuous. So now the basic idea is, the intuition is the PDF, it characterizes randomness over something that's like height, where there are always, finer and finer intervals of possibilities that we could look at. So that's the idea behind that. So one of the things that you'll just want to know for your future, it's not super important, but one of the things that you will want to know is just that the probability of any specific value is exactly equal to 0. So this is something that if you do take a statistics class, they're going to hone this, they're really going to talk about this a lot. It's going to be a focus. So the basic intuition here is that the probability that someone's height is exactly 7 feet 3.117562111111 inches. That possibility is exactly equal to 0. Because you can always subdivide a continuous domain even further and further and further, the probability of any specific event in a counterintuitive kind of fashion is 0. So the basic idea is if you have this interval of, let's say, incomes, the probability of an income exactly being this is 0, because there's such an infinitely continuous, contours of, you can always look at finer and finer gradations here when we're modeling probability in this continuous way. So the insight here is, although the probability of some exact value is 0, we can think still about probabilities within a specific range. So in the continuous case, we no longer think about the probability of some exact event, but what we can do is we can think about the probability of some value falling within a specific range. We'll make precise what that means in a minute, but the basic idea is the fact that things are continuous now means we have to rethink probability a little bit, and we can still think about probabilities in terms of falling within a specific range of outcomes. So this is something that I'll talk about it now, and we'll talk about it next time too, because it's always good to review. But the basic idea is that PMFs and PDFs are similar, but there are some differences as well. And the similarities are that PDFs are going to define relative probability or kind of relative frequency in a similar way as to the PMFs, but now this notion of relative is important. So here in the PMF case, the PMF did define probability, whereas now the PDF is defining some kind of relative probability, and it will take a while for us to learn together to gain intuition for what exactly that means. But so the PDF is going to be very similar to the PMF, but there are going to be a few subtle differences that are going to be important for what we talk about later on. So on the bottom here, I've just listed out various ways that people refer to PDFs as opposed to PMFs. It gets a little bit confusing. So X, remember how X refers to a random variable? That big X refers to a random variable, and little x refers to a specific realization. Now, you'll often see PMFs as being referred to by a capital P, and PDFs being referred to by little p. This no longer, that difference is not realization versus random variable. Instead, this lowercase p will often be used, or this lowercase f will often be used just to refer to the PDF in some abstract way. Just like we had px equals x before, now we have px or px equals x. You'll see different notations. I've listed them out since some of the readings may use one and some of the readings may use another notation, but don't get confused, don't get bamboozled. It's just different ways of saying the same thing. So you'll see these notations, and based on context, you'll now be able to infer which it is. So that's just different notations for it. The most popular distribution, and this will be an important player in this story that we're building up. One of the most popular distributions that are defined over this continuous support is the normal distribution. So just like we had before, a left-hand side and a right-hand side, we have that now too for this new kind of distribution. We have the left-hand side here, px. That's kind of like px equals x from before. So px is the left-hand side, and we have something on the right-hand side. And notice how we have some parameters. Just like we had lambda before when we were talking about the Poisson distribution, we have some parameters now too. And in fact, we have two parameters. We have this sigma, and then we have this mu. So these are sigmas, and this is a mu. And this is what's defining the PDF. You can think of a PDF intuitively as defining relative likelihood. The PMF defined likelihood in some absolute sense, but because of all the nuances with continuous spaces, we can no longer think about absolute likelihoods, but we can define relative likelihoods using the PDFs in ways that we'll continue to explore, continue to explain as we go. So this is an example of a continuous distribution, and we're going to get to know it pretty well since the visualization from the course actually is going to connect to the specific distribution in ways that we'll talk about as well. So this is one example of a PDF as opposed to a PMF, and here are different distributions. These are different normals defined for different parameters. So remember, a parameter defines the shape of the distribution, and here, when we vary the mu and when we vary the sigmas, when we vary that sigma, the distribution looks different, and this is showing you how it looks different. So we'll get to know that pretty well later on, since there's actually a connection between what we're introducing here with the normal PDF and regression, something that you see in almost all these papers, AJ, PSA, PSR, JOP, whatever paper, whatever journal you like best. You flip through it, and a lot of the papers that are there are using OLS, and OLS is actually going to be connected to this distribution that you're seeing maybe for the first, maybe for the second, maybe for the 100th time, but you're seeing it again, and we're going to continue to learn about it as we go. So this is the difference between PDFs and PMFs. It's a conceptual difference. It's an important difference, and we have about 3 minutes. So in the last 3 minutes, I'm just going to briefly introduce something called the cumulative distribution function, which is a way of uniting PDFs and CDFs into a kind of unified language of probability. So the basic idea is the following. given like we can't really think about probability in some absolute sense using a PDF. So is there a way we can still think about probability in an absolute sense for any distribution that you want to work with? And the answer is yes. So some distributions might not have a well-defined CDF, it turns out, or sorry, some distributions might not have a well-defined PDF or PMF, but all distributions will have a well-defined CDF. So a CDF is almost like the universal communicator or the universal translator in the probability space. And what it is as follows. And I've just defined it here. I'm just going to read it, and we're going to come back to it next time since we haven't had time fully to explore it and explain it. But the basic idea is that the CDF is going to give the probability that a random variable takes on a value of X or less. So, and this is just a notation. You'll often see CDFs written with the notation F. I know there's a lot of notation for this, so bear with me. You'll get to know it as we go through this course. But the basic idea is that X can take on a lot of different values, and what we're going to do through the cumulative distribution functions is we're going to quantify, is X less, what is the probability that this random variable takes on a value of X or less. So if you're on the YouTube, I'm drawing a bell curve, and I'm basically asking on that bell curve, what is the probability that this random variable defined over this continuous space takes on the value of, let's say, 2 or less. So we're going to talk more about this next time because we're at time right now. But it's going to involve the PDFs, it's going to involve the PMFs, and we're going to talk about how we can work with these things together to form that universal translator probability. So that's all we have for today. But we'll meet again on Wednesday, and the problem set will also be released today, and we'll go from there. So let us know if you have questions, and thank you for your attention.